Hello and welcome to Dan Explains. It's me, Dan. You've probably heard, especially if you've watched my video on time dilation, that the faster you go, the slower time goes. At least according to Einstein, anyway. Well, Einstein also said everything is relative, which means when you go really fast, it's not like you're going fast, it's like everything else is. So it's not your clock that's going slow, it's like everyone else's clock is going slow. So if you traveled near the speed of light to the next nearest star and back, wouldn't it seem like time barely passed on Earth rather than the other way around? No. Let me explain why. First off, you should watch my video on time dilation as well as my video on what would happen if you fell into a black hole. They will help with the concepts I'm going to discuss here. Links in the description. So, an astute eye will notice one of the things I just kind of glazed over and didn't mention in my video on time dilation. I said that if you were on a spaceship going near the speed of light, time will travel more slowly for you than the people back on Earth, and that when you came back, everyone on Earth would be much older than you. However, I neglected to mention the fact that everything is, as Einstein liked to say, relative. Basically, what that means is, sure, if people on Earth could look at you, they'd see you moving very slowly, as time was barely passing for you. The funny thing is, if you look back at the people on Earth, they would be the ones that seem to be moving very, very slowly. Whose perspective is correct and why? You would think if you were the traveler and the people back on Earth seem to be going through time more slowly than you, that by the time you got back, you'd be the one older, not them. But they're seeing the same thing, so you're the older one. They end up being the ones that are right. If everything is relative, why does their clock beat yours? This seems to break relativity. This is what's known as the twin paradox, because most thought experiments use twins to make the idea easier to understand. Maybe I should have done that. Most articles I've read aren't all that clear about why, but they do mention that the person who ages more slowly turns out to be the one who traveled out to the star and back, since he was the one who had a change in reference frame. The key to understanding this comes from another one of Einstein's ideas, and that is that someone inside of a box would be unable to tell the difference between gravity and acceleration. So let's just say I put you inside of a spacecraft, sitting on Earth, and the spacecraft had no windows. While you were on this craft, you'd be able to walk around like you do normally on Earth. If you launched into space, you of course would expect to be floating around inside the craft since there's no gravity. Well, actually, that's wrong. There is gravity, but you don't feel it because your spaceship is in free fall. But nowhere in that free fall trajectory do you hit the Earth again, ideally anyway. Now, let's suppose you had tons of fuel and you were going to have to travel for years. It would be nice if you weren't floating around all the time. It's not good for your body anyway. So, then, let's suppose the spacecraft designers decided to make the spacecraft always accelerate at 9.8 meters per second every second, which, by the way, is Earth gravity. So, if you were inside the spacecraft in space, and the engineers who built it managed to somehow make the engines completely silent, you wouldn't be able to tell whether your spacecraft was sitting on Earth or if you were in space with the engines on. This isn't actually quite true, as I pointed out in my black hole video. If it were true, either black holes wouldn't spaghettify you, or your spaceship would, if you accelerated at an insane rate anyway. But neither of those are true. However, you can pretty much ignore those forces at 1g of gravity, or acceleration, because those forces are really tiny. Anyway, back to the point. If you were on a spacecraft, you wouldn't be able to tell if the engines were on while you were flying through space, or if you were sitting on the ground with them off. This is because acceleration and acceleration due to gravity are the same thing. And yes, even though you don't think you're moving, you are accelerating right now, assuming you're not watching this floating in space anyway. If you weren't accelerating, you'd be able to push off of the Earth like you were floating in space. So, the whole key to this is hidden in one of the examples I used in my time dilation video. When I was talking about the GPS satellites, I mentioned that they were experiencing two types of time dilation. Time dilation due to them moving really fast, and time dilation due to gravity, which I said more than canceled out the time dilation due to speed. Basically, the deeper in the gravity well you are, the slower time goes. The higher up you go, the faster time goes. So, the clocks on GPS satellites are actually ticking faster than ours here on Earth, since they are higher up and further from the Earth's gravity well. And they are experiencing less gravitational acceleration than we are. So, it's the acceleration, not the gravity itself, that is causing the clocks to tick differently. Now, let's go back to the example of traveling to the next nearest star. I say next nearest because our sun is the nearest star. Let's assume you don't accelerate the whole way, but you speed up to near the speed of light over a few days or weeks or something like that. Then coast most of the way and then turn your ship around and come back the same way you took off. That way, your journey looks like this: acceleration, coast, deceleration, which is the same as acceleration, acceleration, coast, and deceleration again, at which point you're back at home. For you, on the spacecraft, during those two coast phases, the time back here on Earth would seem like it was going more slowly. However, during the acceleration and deceleration phases, the people back on Earth would be like the GPS satellites in space, only much more extreme. During those phases, their clocks would seem to be moving extremely fast from your point of view. It would be like you're in a gravity well even deeper than they were, even though you're flying through space. These phases of accelerated time you experience would more than cancel out the period of accelerated time you experience during the coast phases. So once you got back to Earth, time would have accelerated so much your clock would be way behind theirs and would exactly match what they were expecting. If they could see your clock the whole journey, besides the turnaround, since the time would be momentarily going the same rate, your clock would be going slower the whole time. So the negative time dilation experience during acceleration is the key to understanding why the twin paradox isn't a paradox at all. If you like this video, please press the like button, subscribe to my channel, and ding the bell to get notified when I post new videos. Also, please support me on Patreon, link in the description. The more people who support me, the more time I can dedicate to making videos like this one. So, until next time, have a great week.